We will do a sample reduction proof very soon, but to be able to do that, let us learn a new primitive, pseudo-random generator. So pseudo-random generator, PRG. A pseudo-random generator, let's say G, is a function, let's say, that has an n-bit input and some n prime bit output, such that n prime is strictly greater than n, and n prime is indeed some polynomial in n. Such a G needs to be a polynomial time deterministic function. This is very important. A PRG, a pseudo-random generator, is a deterministic algorithm or function. Okay? So it's not randomized. It is going to produce something that looks random, but it's going to produce it in a deterministic way. The security definition for a PRG is as follows. Now, we will say that, as usual, for all probabilistic polynomial time, let's say adversaries or distinguishers, let me call it D, there must exist a negligible function, let's say neg n, in terms of the security parameter n, such that, now what's the probabilistic experiment? In the first experiment, we will pick a random seed S from the domain of G, so from n-bit values. And then what we are going to do is we will compute R, which is G of S. So we run G on this random seed S. It will give us back some value R. And then we will give this value, okay, first of all, let's say the security parameter. I can explicitly write G here, okay, so I can say, for example, that this distinguisher knows this function G, but remember, functions are always public, only keys are secret, so I don't need to explicitly write it. And then I'm going to give this value R to the distinguisher. It will tell me either random or pseudo-random. So let's look at the probability that I pick a random seed, compute G of that, and give the output to the distinguisher, and it says random. Okay. And on the other hand, I will look at the probability that, now I am not going to pick a seed and run through G, but I will still compute a value R, but I will pick it uniformly randomly. Now, if I pick it with a different length, it's very easy to distinguish. So I will pick it of the same length as the output of G. So I will pick an n prime bit random value R. I will again give this to the distinguisher together with the security parameter. And I will look at the probability that the distinguisher says random in this case again. So I give it a pseudo-random value, the distinguisher says random, and I give it a random value and the distinguisher says random. What I want is that these probabilities are negligibly close. So one is, let's say, plus minus neg n of the other. That is the security definition for a pseudo-random generator. On one hand, I am picking a random seed, running it through G, obtain a pseudo-random value, give that pseudo-random value to the distinguisher. The distinguisher thinks that it is random. On the other hand, I really pick a random value of the same length, okay? as the output of G and give it to the distinguisher, and the distinguisher again thinks it is random. And I want these probabilities to be negligibly close, meaning that the distinguisher indeed cannot distinguish between pseudo-random and random with better than negligible probability. One very important thing that people keep forgetting is that a pseudo-random generator produces random-looking outputs as long as the input seed is random. That is very important. If the input seed is not random, this PRG security definition does not provide us with any security. It provides us with indistinguishable from random output of the same length only if our input was itself random. Now, from this, what we are going to do is we are going to do something like a one-time pad, okay, such that now we can encrypt a longer message. So let's call it PRG based encryption, okay, and our encryption algorithm will look as follows. Remember, to define an encryption scheme we need four things. One, key generation. So we need a gen algorithm that outputs a key k. And how this will work is that indeed our algorithm, so this algorithm will just pick a random key that is from the domain of this PRG, so n-bit random key. We need an encryption algorithm that takes this key and a message in the message space and produces a ciphertext. It will work as follows. It will compute G of our key K, and then, as in one-time pad, it will XOR it with the message M. And this will be the resulting ciphertext. When we want to decrypt this ciphertext using the same key, what it will do is it will again compute G of the key K. Now it will XOR it with the ciphertext and return the resulting value. Because XORing a value with itself results in all zeros, it actually cancels it out. This is a perfectly correct encryption scheme. The next thing we are going to prove is the following. So our theorem would be, if G is a secure PRG, okay, then this encryption scheme here, and we forgot to define the message space. What will be the message space here? As you can guess, it is all n prime bit messages. Remember, G of K will be an n prime bit value. Okay, so let me call this scheme, let's say X. We will prove that if G is a secure PRG, then X is a secure encryption scheme under single message, okay, one message. We will get into this maybe later. Eavesdropper, okay. So remember the eavesdropper security game that we defined. We already defined it for a single message actually. So X will be secure under that game. We are going to prove this next.